Chapter 5, Section 2 in the 7th grade textbook is entitled Interpreting Graphs. What this section is about is, or rather what is going to happen here, is they're going to give you a situation in words, in essence a story problem. And what you're going to do with that story problem is you're either going to make a graph that matches that story problem, or you're going to be matching that story problem with a selection of graphs. It's not so much about the numbers here as making sure that the graph is logical. For instance, if I say the height of something is increasing, that means I need to see the graph going up, because the only way for me to show the height getting bigger is for the graph to go up. If I say the number of hours spent on a project is decreasing, that means I need to see the graph going down, because the only way to show decreasing is going down. It may not give you an actual number here, so you just have to have a graph that makes logical sense, which is exactly where they're starting here in question number 1. If we take a look at question number 1, it says the height of a tree increases over time, but not at a constant rate. Which graph best shows this? Well, as you can see, both these graphs are comparing the same thing here. They're both comparing time and height. So both of these graphs show time happening, and this particular graph shows the height, let's say this is at 4, is always at 4. But here it shows that the height starts at nothing, but then gets bigger to 1, to 2, to 3, to 4, to 5, to 6, assuming this graph goes by ones. All right, well, let's look at what the question says. It says the height of the tree is supposed to increase over time. So as time happens, that number for height should get bigger. And indeed, this is the graph that shows that. Do we know exactly at what amount? No, not really, but that's not relevant. This graph does not show that. This shows time is happening, yes, but the height of the tree never changes. So obviously graph B is going to best show this. As the tree grows, its height is increasing, and then it will reach its maximum height. Graph A shows the height of a tree not increasing but remaining constant. That's another way we know that A is not correct. This part here says it's not a constant. Well, remember, any line, horizontal, vertical, diagonal, that's constant. This is constant. This is not a line, so this is not constant. Or, in other words, variable, if you remember from when we were talking about constant and variable. So here, since this one is also not constant, that's another tip-off that B is the correct graph. Continuing with the solution at the bottom there then, graph B shows the height of the tree increasing at a constant rate, increasing not at a constant rate, it should say. Graph B shows the height of a tree increasing but not at a constant rate and not reaching a maximum height. So the answer here is going to be graph B. All right, let's go ahead and continue on here. Number 2, Jared parked his car in the supermarket parking lot and walked 40 feet into the store to the customer service counter, where he waited in line to pay his electric bill. Jared then walked 60 feet to the back of the store to get 2 gallons of milk and walked 50 feet to the checkout near the front of the store to pay for them. After waiting his turn and paying for the milk, he walked 50 feet back to his car. Sketch a graph to show Jared's distance from his car over time. Use your graph to find the total distance traveled. All right, so if we take a look at this question, the first thing they're going to do is break this question down into pieces because we're about to graph it. So the answer here is the distance Jared traveled. The question in the very last line is asking me to find the total distance traveled, so that makes sense. Then they're going to go ahead and list what we know. That he walked to the customer service counter, that he then waited in line, he walked to the back of the store to get the milk, he comes back from the back of the store towards the front to check out, where he then waits in line and then walks back to his car. So that's the situation we're going to graph here, and we'll use that graph to find the distance he traveled. Now, as far as the elements of that graph here, we're going to see the distance increasing as Jared walks to the customer service counter. Remember, the starting location is his car. So as he gets further away from his car, we're going to see distance increasing. Anytime he goes further away from it, the distance is going to increase. When Jared waits in line, though, that distance isn't going to change. Whether he waits there for 2 seconds or 5 minutes isn't really all that relevant. It's just we know that that distance is not changing because he's not moving. He's going to go to the back of the store, so the distance is going to increase some more. Because again, he's getting further away from his car. But then he's going to come back towards the front of the store to check out. So finally, we're going to see the distance decrease there because he's coming back towards the direction of his car. He's not coming all the way back to his car yet, but he's coming back to the front of the store, which is closer to his car. He's going to wait in line again, so the distance is going to remain constant. And then the distance is going to decrease again as he gets back to his car. And of course, it's going to come all the way back to 0. So as you can see, we've got a graph here. Now, taking a look at this graph, it kind of goes to what I was talking about in the introduction here. If we take a look at the x-axis here, never in the situation do they say anything about time. So you won't see any numbers down here on the time axis. We know time is happening, so that's why we see the graph going forward. It has to be happening. But how long he exactly spends to walk to the checkout line or walk to the back of the store, we don't know. So as long as we show time happening here, we can't be wrong on the time axis. Now looking at this y-axis, this represents the distances. We do have distances there, so they throw numbers on here. There might be this problem where they don't actually give you those distances. And if they don't give you any distances, then you just have to go with what you have. So it says in the beginning that he starts off at the front of the store, or his car, and he walks to the customer service line, which is 40 feet away. So you can see this point here, the origin really, this is just quadrant 1 of a graph. The origin here is where he starts, that's where his car is. He's going to walk 40 feet to the customer service counter, so that's why the graph is going up to 40 on the y-axis here. Then he's going to wait in line. So that's where the graph is showing flat. Time is passing, happening, whatever you want me to say, but whether it's passing or happening, what's not changing is how far he is away from his car because he's waiting in line. So that's why it's flat. Then it says he's going to walk another 60 feet to the back of the store. So all of a sudden it goes 60 further away from his car, and we get out to this point here. So obviously the graph is topped out here at 100 now. After he grabs the milk, it doesn't really take him any time at all. He just grabs the milk. He's going to walk back towards the cashier. That's 50 feet towards the back of the store, towards the front of the store rather. All right. Well, I don't want to show the graph going this way now because if the graph goes this way, this means he's getting further away from his car. He's not getting further away from his car. He's coming back to the front of the store. His car is in front of the store. So that's why the graph turns down now and shows him 50 feet closer to the front of the store, 50 feet closer to his car, really. So the graph comes back down and it comes over to the 50 line here because he's walked 50 feet back from 100 to 50. All right, now he's going to wait in line to pay. So again, the graph is flat here. And based simply on this line, we don't know this for a fact, but we're going to base it on how they drew this, that he must have waited in line longer to pay than he waited at customer service because the line is obviously longer. And then after he pays, he's going to walk back to his car, which is distance 0. And there's your graph. Now your graph might not be exactly like that. Your graph could be a little bit wider or it could be skinnier. Is it still accurate? Yes, absolutely. What doesn't change, all right, are these relative heights. The top mark here, no matter how your graph is, has to be 100. All right, this mark here, where it shows how far he walks to the customer service counter, has to be at 40. This mark here, which shows the distance back from getting the milk to the cashier, has got to be 50. Those don't change, but your graph can be wider or skinnier and still be accurate. So after we make our graph then, the question is, what's the total distance you traveled? Because that's what the question was asking me to find. Well, he walked 100 feet to the back of the store and then 100 feet back from the back of the store to his car, so the total distance traveled there is 200 feet. All right, finally we'll take a look at the last question here. The dimensions of the basketball court have changed over the years. However, the height of the basket has not changed. Which graph best shows this? So, notice these graphs look very similar to the original example here because they are the same graphs. What they're showing here is that the dimensions of the basketball court have changed, but the height of the basket has not. So the height of the basket has remained constant. It has not changed. Which graph shows this? Well, both of these graphs, again, as we discussed in example 1, show time happening. Time is clearly happening no matter what situation we're looking at. But what's not changing is the height. Well, as you can see, this one shows the height starting at 0, but increasing. Well, that's not what this situation says. It says the height of the basket has not changed. This one here shows the height of the basket at all points in time is exactly the same because its y-coordinate value is exactly the same. So graph A is the one that shows the height of the basket not changing, but time indeed passing.